Right, so we have new slides here, and before we do these new slides, let me tell you that I was, not last night, but the night before, I was trying to sleep. And I started dreaming of a problem that I could give you for your test. And it kept me awake. So I got up and I wrote it up. All right, so it's a little, it might be, like many problems, it's going to have a bunch of fill that's going to scare you, but the actual questions, I think, are pretty straightforward. All right? And let me tell you that they're pretty much identical to what I'm going to show you right now. All right? So I really, really want everybody to get perfect. You just, come on, guys. Don't get scared by, I'm going to talk about various things, but, you only need to know what you need to know to answer the question. And, and then I haven't made it up yet, but I can pretty much assure you what the second question will be. And maybe there'll be more, but maybe that will be long enough because you only have an hour and a half. All right, so the second question is probably, and I haven't made it up, I'll give you some Java-like code, and you will compile it into a Turing machine. Right? Those are two problems. So, all right, now let's do this. And I've become, partly I was always obsessed with first order logic, but then I started trying to think about 1090 and this course. I become more and more obsessed with first order logic. All right? So what did we do last class? We defined various models of computation. Right? We had the go-to model and the single loop model and the various models of computation. Right? And so now I'm going to define a new model of computation, and it's going to be called the table lookup model, and then we will relate it to Turing machines. All right? So, and I like Winnie the Pooh. In fact, part of the reason I was tired is that my girlfriend has been sick, and so I was reading Winnie the Pooh to her, and she was keeping me up all night with her fever and with your math problem. So anyway, here we are. Here's our model of computation. It's going to be a table lookup. And what does that mean? Doesn't feel like computation, table lookup. But let's think about how we're going to use it. Remember, what is a model of computation? It tells you what a legal algorithm is. And what is a legal algorithm? It steps. One thing it needs a finite description, right? And my table is going to have a finite description. And it's going to have rules for calculating, right? And these rules are going to be about the simplest rules ever. The rule is the algorithm is a table that lists input-output pairs, right? And how do you compute? Well, if you just look up the answer, right? If the input is you give me an input, and if it's in the table, I give you the answer. And if it's not in the table, then then I fail. Right? Everybody get the problem? You can't have an easier model of computation. But it's always good to know, right, what the various things are. Now, of course, this model of computation, if I allowed you to have an infinite description, right, then I could solve anything, right? So that's why we require our description to be finite. All right, so now let's just say this is going to be exactly the same as we did before. Nothing new here. We're going to say various things about what you can and can't do with this, right? So here, can you use table lookup to multiply two arbitrary real numbers in one time step? Right? Can you do that? if you haven't noticed, this is multiplication, right? So I'm going to say yes, right? Yes, sure. How do I multiply 2 by 4? I look at it in the table, it's there, right? But then this guy, he says, oh, but I can't multiply 2 by 5, right? It's not in the table, right? So we're trying to get the sense of what you can and can't do with this table lookup. So here's a first order logic statement, and we want to understand, this is where I'm really hoping everybody at this point in this course, you can read this, know what it says, and know whether it's true or not. All right? How many people understand this kind of stuff? How many people are still losing it? Not quite getting it? All right? Right, so this is, when I say this is what's going to be on the test, is understanding this kind of thing. All right, so there are various ways that we can understand this sentence. The one is a game, right? I'm trying to prove for all k, so I provide a k, right? And then, oh, no, sorry. See, you should have corrected me. I want to prove it. The adversary wants to disprove it, right? So the adversary gives me a k, right? Let k be an arbitrary k. And then I want to prove it, so I go next. We could read them in order. The exists, I go, and I come up with, I know k, and I construct a table, right? So my job is to build a table, right? And then the adversary gets the for all. Right? Now we're questioning, can my table compute? Can it compute multiplication? That's the question, right? But we've limited the adversary. The adversary has to come up with an input, x and y, and those x and y need to be limited by k, right? And then I win if my table M, can multiply the adversary's x and y together, right? That's the game. Everybody understand the game? Now, so the game you should just be able to read off, and then you have to think, can I win this game? Do I have a strategy in which I can win this game? Right? Now, let me go another way of saying it, right? And I don't know if this is, whether it's useful to do it the two different ways, right? The other way of doing it is, building it out, right? The inner statement, we have three variables. There's capital M, which we know is a table, and X and Y, which we know are questions. And the question is, can I multiply X and Y with this table? So the question is, does the input X, Y, is it in the table, right? I win if it's in the table or not. I mean, that's the question. Right? And those are my three variables. So we know what the inner thing means. It means, are these x and y in the table M? So then we can go out a level, right? We include the for all x. So now our free variables, our k is k and M, right? We want to say something about k and M, a sentence. Tell me something about k and M. And what we're saying is, can you multiply, right? Does M have the property that it can multiply every pair of integers that are bounded by k? Right? That's a question, right? We're trying to say something about M and k, a property of M and k. And the property is, M can multiply every pair of numbers that's bounded by k. Right? Everybody see that as a property of M and k. So then we can go out further out, and now we only have k as a free variable. Right? So we're asking, is there a table? Can tables multiply x and y as long as x and y is bounded, right? And then we go further out and we have no free variables. And the question is, can I multiply in this model of computation if my inputs are bounded somehow? Right? Everybody got this as a question? Can I do bounded multiplication? Right? For example, your computer. Does your computer do bounded multiplication? Right? It can probably do either 16 or 32-bit multiplication, bang, in hardware in one time step. Right? And how does it do it? It's not table lookup, but something, right? So everybody get this? And so is this question true or false? It's true. Everybody understand it? Right? Can you do this on a test? That's the question. Right? Yeah? Yeah. Yeah. I try to make the slides as easy as possible without saying things that are wrong. You got the idea. Bounded, right? All right, so here we're going to prove it's true, right? The blue guy is going to try to prove it's true. So how is he going to prove it's true? Well, for all k, who's going to come up with it? The adversary. We're going to say let k be an arbitrary integer, right? Now we have k. Then the blue guy is going to have to come up with a table, right? I give you a multiplication table. How big is this table? It's the size k squared. Actually, we did this. Now I'm remembering that we did this right over here, right on the board during the tutorial, one tutorial, right? So everybody get that? You build. How big is the table? It's the size k squared, but it's still finite. I can build it, right? Everybody agree? And then the adversary gives me my x and y. I give them the product. We're good. Everybody got this? Yeah?
Okay, so k is what restricts your x and y.
Yeah.
But like this table doesn't seem right because it seems like
It's not symmetric?
no,
X.
so like it seems like you go your one is x.
Yeah.
And then
Yeah.
x is one.
Yeah.
And then
I'm not saying that that's even an example. One, I need it to fit in that little, I need it to be big enough that you get the pattern and to fit on the slide. So I'm not saying that's an example of what we're doing here, right? Maybe x was only 2 and I made the table bigger for good luck. I don't know. Yeah?
So the main thing there would be that x and y are bounded by the table. Both
Yeah.
of them are bounded, not
Yeah.
just and y.
Yeah. Yeah, they're both bounded because we need our table to be bounded. All right, everybody good with this? Yeah?
what would be the difference if you like choose all k or some k? Would that make a difference in the statement? Like in the very beginning?
Well, it would say something very different, right? If there exists a k, then when I want to prove it, I have to come up with a k, and I could make k be 0, right? So it's much weaker statement, right? That there's some bounding in which I can multiply, right? But this is much bigger, right? We're saying every integer k, no matter how big it is, there could be a table out there, right? And this is kind of the big O of 1 stuff, right? I'm saying how you can make your constant as big as you want, but you got to choose what it's going to be, and then we're going to get the input later on, right? So it's all this. Everybody following how we're doing this, right? And this is kind of what we're going to do with Turing machines as well. So now let's say a different statement. So everybody read this and tell me whether it's true, and could you prove it on a test that whether it's true or not? We got more falses, right? What is it saying now? All I did is the exact same statement. we remove the bounds of k, right? So it says, can I multiply, right? And I've had this discussion, I've been teaching for a while now, so I've had this discussion so many times. And this is why I get more and more pounding the first order logic, right? People will say to me, well, I can multiply 1,000,000 times 1,000,000 with a table. I just have a table that has 1,000,000 times 1,000,000. I can multiply 1,000,000,000 times 1,000,000,000 with the table. I just need a table that has billion. Right? So I can multiply anything with the table, right? People get very excited. I get excited. Everybody following how we're getting excited? So this says, can you multiply anything with the table? And it is true. For every pair of x and y, I can build the table so that you can multiply them. Right? Everybody agree with that? For every x and y, you give me a trillion times a trillion, I can build a table that's big enough so that it covers everybody up to a trillion times a trillion. I can build it. Right? So can I multiply everything? No. No, you can't multiply everything because everything's a lot. I can multiply any subset of everything. I just can't multiply everything. Right?
The issue of the fact that, if I'm understanding right, is the issue that even though you can make a table that goes on to infinity, at that point you have to stop, and your adversary doesn't. So
yeah, exactly. Well, no, I can't build it to infinity.
No, like I'm saying,
I can build it.
Infinity, but you'll have to stop eventually before the program can even begin.
Yeah, I mean, it's back to, remember the very first day of this stuff, we played the game where you came up with an integer, and your integer can be as big as you want it to be. But my integer is going to be bigger because I go second. Right? So if you come up with the x and y first, then I can make my table big enough to handle your x and y. Right? But if I had to come up with the table first, I can make my table bigger. I can make a big table. But you get to come up with x and y second, and you can make them bigger. Right? It's all, George says he doesn't play games, but to me it's all games. Right? This is not true. I can't multiply arbitrary x and y in one time step. I just can't. Why can't I? Because, right now I'm trying, I keep trying. I come up with a table. But it's finite. So then the adversary says, hey, your table better be finite in size because we don't like infinite tables, right? Moreover, if it's finite in size, it can't list every possible pair of answers, right? It can't. And so there must be some pair of inputs that you didn't list, and I'm going to give them to you. Everybody get that? Right? Are you getting this game? All right. Any other questions about this? Because really, this is what I'm wanting you to learn this game. All right? Because to me, it's theory of computation. Right? All right. So now, in fact, I was just having a discussion with my father yesterday. He sent me this little article about scrotum function, not scrotum. Somebody else, some mathematician. And the little paragraph said, well, he developed this and this and this, which was basically this. And hence, he pretty much single-handed developed theory of computation. I mean, that's what the paragraph said. All right, so anyway, let's do it here. Right? Turing, much later than this scrotum guy. Right? So Turing says he's going to define a model of computation. Right? And his question is, well, what should it allow the machine to do in one time step? Right? He needs to define the model of computation. He needs to say, what can it do? Right? And so he asked the question, should it be able to multiply, for example? Right? Is it fair to multiply? Right? In one time step. Well, now these are people from the future are saying, right, some CPUs have built-in hardware that can multiply 16-bit numbers in one time step. You know, we feel it's fair, we're doing it, right? And so you can do it in one time clock, one cycle of the clock, right? And then this guy says, yeah, but we can only do 16-bit numbers in your hardware, right? If you want to multiply bigger numbers, now you need software and more time step, right? Right? And then you can also say, well, there are other types of CPUs, right? They don't let you do fancy things like this. They have very simple operations. Why? Because they want their clock to be faster. You're going to do something fancy like that in a clock cycle, then you need a slow clock cycle. If you only let you do really simple things, and you need a really simple things, you can have a faster clock cycle. Everybody kind of get that? There's these trade-offs. And poor Turing, he says, well, I didn't know any of this back in 36, right? So what he decided to do is he was going to let the algorithm designer decide, right? Do I allow 16-bit multiplication in one time step? If you want, you can. It'll make your clock cycle slower. Or you can have simple ones. You can build anything you want into your machine. The algorithm designer gets to allow the machine to do anything in one time step as long as what? There's going to be one requirement on it. It's finite. In fact, look at what's written in yellow. Right? As long as it's described by table lookup. Right? You can build any table into your machine you want. Right? That's what he said. The algorithm designer is going to design this code, and the algorithm designer is going to start by saying what you can do in one time step. And the way that that's going to be done is by providing a finite table of input-output, right? Right? And so there's your table, right? And the adversary says, anything? I can do anything? Okay, great. I'm going to solve the halting problem, right, in one time step. Can we do the halting problem in one time step? Yes, no. It depends on how you word it, right? Right? It's okay. You can solve the halting problem one time step as long as you can build it into a finite table, right? If you bound your inputs to be so that you can do it in this finite table, you can do halting problem, right? In one time step. All right. So here we're going to just repeat the slides we had before, right? In fact, I copied slides over, right? Can a Turing machine solve the halting problem? Well, Turing proves that it can't solve the halting problem, right? We're going to prove that. But you just said you could solve it, right? So let's try to understand it again, right? Is this true? You should recognize it, right? Is it true that for every k, there exists a Turing machine? Right? You give me an arbitrary k, I build a Turing machine. Right? The adversary gives me an arbitrary input to the halting problem as long as the size of the input is bounded by k. Right? And then my Turing machine, not only does it solve the halting problem on your input, but it does it with table lookup in one time step. Right? Is this true? Right? This is true. Right? You give me a k, I can build a Turing machine that has the table lookup built into it. Right? Does that make sense? You can think about it as, I talk about it as what's built into your hardware that you can do in one clock cycle. Right? right? Maybe your hardware is not quite table lookup, but it has AND gates and OR gates that's storing it for you, right? All right, sure. Why? You give me a K, I build a Turing machine, right? I give you the halting problem table of size K built into my Turing machine, right? Now, when I was making these slides, I got philosophical. So we're going to have a couple philosophical lines here, all right? One philosophical line is, well, how did you build this table? Here my blue guy says, you give me an arbitrary K, I'm going to build this table. Well, dude, you can't build it. Why? Because the halting problem is undecidable, right? How did you compute the answers to put the answers in this table? It's a question, right? Right? So the blue guy says, yeah, good point. All right. All right, so he tries again. He says, there exists a halting table. I'm not claiming I can build it, right? I'm not even claiming there's a fairy godmother or a god out there who can build it, right? There exists this table. And the red guy says, well, I don't know what planet you live on, but I doubt there's such a table anywhere, right? And then he tries, right. So he tries again. He says, well, of tables of size K that list answers, there are 2 to the K possible tables out there, right? None of them necessarily exist, but imagine all 2 to the K of them. One of them happens to give the right answer, right? There are 2 to the K of them. One of them gives the right answers, right? And so does it exist? Well, theoretically, it exists. Everybody with me here? Oh, well, I'm imagining that your input is 1, 2, 3, 4 up to K. So the table just has to answer yes, no, yes, no. So there are 2 to the K of them, right? It doesn't really matter. There's some number of them, right? Yeah?
Why couldn't the Google algorithm just run those inputs to its finite, right? What if you run them and find out the
Wait for the halting problem thing. So I got a Turing machine. I want to know whether it halts. Why can't I just run it and find out? Well, I run it. If it halts, I say, great, it halted. But if it doesn't run, if it doesn't halt, how long do you run it before you say it doesn't halt? That's our problem, right? All right, everybody getting this? Right? This table is out there somehow in the existence, fairyland. And so then when you give me an input of size K, if K is smaller, I can do table lookup. Everybody good? Yeah?
But isn't this table kind of useless? Like, yeah, it does the thing that it wants, but it's only going to give you the yes or no at that point. Like,
Up until K, but then your computer is useless. It only knows how to multiply 16-digit bits numbers together, right?
I'm just confused, like, why is that table in particular better than the other one? Like you mentioned the table before.
Yeah.
Just being like, there exists a table, and the guy said, I doubt that.
Right.
And then he came up with this table.
Right.
So why is this table a viable answer to the thing? Like, I get that
Oh.
mathematically, yes, it will get the correct answer eventually at some point, but why is that?
You're asking why does this table prove this statement?
No, I'm asking why is that table,
If you had it, why would it be useful?
yeah. That's
Well, if you had it, you could solve the halting problem for all inputs of size less than K, and we're later going to talk about reductions, that if you can solve this, you can solve this. And if you can solve the halting problem, you can solve any problem. And it would be useful to be able to solve any problem on any input of up to a billion, right? It would help you figure out how to do great things. It's a useful table, right? Now, does it solve the halting problem? No, it only solves it on
on a certain value, like up.
up to a billion. Then it cuts off, right? Yeah.
I think his question was, like, you presented the same argument,
Right.
three different ways,
Yeah.
but this is the way that's right, and the other ones were wrong. So I think that maybe might be your question.
Well, I didn't say wrong. It's the way I would do it.
Yeah.
Right? It's the way I told you to do it. It's say, I'm going to give you this table. I only put in these nuances in case people wanted to argue with me. I was one step ahead. Right? What does exist mean? Right? We're getting into philosophical discussion. Do pink elephants exist? Well, I can imagine a universe where there are pink elephants. I can imagine taking an elephant and painting it pink. Is there currently on this earth a pink elephant? I don't know. But, I mean, we can talk about for something to be computable, there needs to exist an algorithm that can compute it. Doesn't mean I know how to code it up. Right? I mean, I was just bringing the philosophy into it. Right? And in fact, sometimes there are proofs that things exist where you don't know how to construct it. In fact, here is an example where I'm kind of proving it's what I call non-constructive proof. Right? If we were doing multiplication here, no one would argue that I would be able to produce this table. Right? But now I'm talking about a table that I don't know how to produce, but I'm arguing that it exists. Right? So it's a non-constructive proof. Everybody good with the concept? Yeah. All right, now is this true? Clearly not, right? Clearly not. I have a finite table. It better be finite. Dude, you can't do it. Oh, here I didn't even change the slide, right? I cut it and pasted it without fixing it for multiplication. Everybody good? All right, so now we're actually going to, I think I did these slides already for you, right? These were the motivations. Turing machines, they're simple machines, and it's cool that they can do everything, right? And emergent property, right? We're talking about you need to define what can be computed so we can say the halting problem can't be computed, right? And just like a proof system, they want the simplest possible. And whatever the scrotum guy's name is, we should put him in here because I had never heard of him until a couple of weeks ago, but he actually did some pretty great things. Right? We want the simple machine. So, right, and here, right, if you gave all of multiplication away in one time step, it feels like you're cheating, right? So what are you allowed to give away? You're allowed to give bounded multiplication away, right? It's cool that you can compute everything. It's definitely not practical, right? You're not going to go home and write a video game in a Turing machine, right? You're just not, right? So this is just reminding us again, computable. This is reminding us about compile time versus runtime. All right. So again, Turing machines are going to have some things that are fixed in compile time and some things that are fixed in runtime, right? And remember, compile time is what you know before you have the input, versus runtime you have the input, right? So it says there exists a Turing machine, right? So what do we know at runtime, at compile time, right? Right? We have to know. We don't know the input, right? It needs a finite description, a finite set of instructions, a finite set of variables. Right? Each variable is going to have a finite range, right? What I didn't add here, I should add here, it's going to have a finite table lookup to tell me what to do next, right? This slide was created many years ago versus the table lookup was created a couple of days ago, right? Everybody good? Right? Versus now at runtime, right? Now I know the input. Right? So and I choose the input after I know the machine, so it can be much, much bigger. Right? You can have your table, at compile time, I can build this table lookup. But then at runtime, the input's going to be much, much bigger. Right? And what do you need? Well, you might dynamically have to create more memory, right? And you might dynamically need more time. And so that's what we're talking about here. Everybody following this? All right, so what's a Turing machine? That's a Turing machine. At some point I Googled Turing machine and I downloaded this little image, and I'm surprised it's not running. It used to run. I don't know why it's not running right now. It's a GIF that runs.